So for derivatives, we have rules. You know, we have the product rule. We have the quotient rule. We have the chain rule. And these rules, no matter, they work no matter what. But for integration, there are no rules, okay? If you are given any function, you can find the derivative of that function, no problem. How complicated, no matter how complicated the function is, you can find the derivative of it, but not integral. As a matter of fact, if you are given a random function, if you're given a random function, the chance that you can integrate that function is 0, almost 0. There is almost a 0% chance that you can integrate a function, okay? For instance, like let's say you have the integral of e to the x squared, a very famous antiderivative, okay? There is no function, it turns out, there is no expression whose derivative is e to the x squared. There is none. There is no such thing. We can't do such thing. Anyway, okay, so when you get to calculus 2 and calculus 3, one of the main objectives of those courses is to integrate, okay, or find antiderivative. So let's look at the material for day 5. Question 1 is about Riemann sums. I think you guys are more or less familiar with Riemann sums. They play a role for finding a definite integral. I'm not gonna go over Riemann sums. I'm gonna go over the tools that you guys need in order to be able to integrate or understand integration, okay? Yeah, so going with certain properties of integrals. So for instance, look at problem 2. Okay, problem 2 for the properties of integrals. You are given a piecewise function. Okay, it's x from negative pi to 0 and sine x from 0 to pi. How do you propose that we find the integral of this function? Anybody? So a piecewise function here. What do we do to, let me see if I can copy and paste this thing. Give me a second. Yeah, so right here. Yes. Any ideas, you guys?
I don't know if I am right again, but you take from negative pi to 0 the first piece of the function and integrate that, and then I don't remember if it's adding or multiplying. I don't remember, but and then the second piece from 0 to pi. But I don't know if it's correct.
That is absolutely correct. Yes. So we have two domains of, we have a piecewise function, okay? If I can actually graph this thing, let me do my best to graph. All right, so here we have from negative pi to pi. Yes, so from negative pi to 0, it's the line y equal to x. Well, y equal to x looks something like that. It's just a line. All right. From 0 to pi, the graph is sine x. Well, sine of pi over 2 is 1. Please make sure that you guys can find the can graph basic trig functions. So it looks something like this. Okay. Yes. So this integral, the integral here, is going to break into the integral from negative pi to 0 of the function here is x, in addition to the integral from 0 to pi of sine x. Okay, and we all know how to integrate those, right? I don't need to do the integral for you. We know how to integrate these functions, correct? Yeah, so that's that problem.
I didn't understand that.
It's my phone. My phone is just so stupid. It doesn't understand anything. Do you guys hear that? All right, so that was problem, I think, 2. Next problem. Okay, what about problem B? Problem B, integral from 0 to 3 pi over 2. So 2b. And the function is absolute value of sine x. Yeah, some people just drop the absolute value. I don't know why. But to answer such question, do not disregard absolute value, because sometimes your integral represents a certain quantities, like area, for instance. Okay, so if you were to graph absolute value of sine x, or just sine of x itself, sine of x from 0 to 3 pi over 2. So here is, let's say, pi over 2. Here is pi, 3 pi over 2. Case the roots are at 0. We have a maximum at 1, root at pi, and minimum at 3 pi over 2. Okay, so the function like that, and then below the x-axis, like that, right? So when we say absolute value of sine x, the output has to be positive, okay, which means that this part is troublesome. It has to go up, right? So the way to do this problem is to break this into two. Remember, you guys, absolute value of something is piecewise. It's piecewise, positive, negative. Okay, so we shall break this down to the integral from 0 to what? 0 to pi of just sine x dx. Okay, then plus, okay, what do I do for the integral from pi to 3 pi over 2. Any suggestions? How do you make that negative part positive? Any questions? Any ideas?
You flip the integral?
Yes. You negate it. If you do negative sine x, okay, you're multiplying this negative part. This negative part gets multiplied by a negative. Negative by negative makes it positive. So this is going to happen. All right. Now the whole function is positive. You see? So multiplying this part by a negative makes it positive. That's why you need that negative right there. Okay? All right. Yeah. Yeah, and then you do this problem. So if you were to do this problem without the absolute value, then you're finding this area which is positive and this area which is negative. Okay? Then this, which is symmetric to this, would cancel out, and the answer would just be this, which doesn't make any sense at all. Okay? It doesn't make any sense at all. So this is what you have to evaluate. And I want you guys to actually complete that problem. All right. Here is a very important problem. All right. This problem I used to put on my exams in Math 7. This problem gives you bounds for a function. It gives you, bounds for an integral. Okay? Let me actually also copy and paste this onto the notepad. Very important property. When you're doing numerical analyses, you always want to find bounds. What does my value exceed? What does it go beyond? What does it go above? All right. So let's pay attention. This integral is from -1 to 1. All right. Let's say, forget this function for a moment. Let's say we have a function. Okay. So let me graph that. Oops. Here it goes. All right. So we have a x and y. Okay. So let's say this is A, this is B. Okay. And let's say we have a function over A to B. Let's say here is that function. All right. What do you see about this function? What's one of the most important things in calculus that has to be true about functions?
Continuous?
Yes,
Continuity.
very good, continuity. So important. You have no idea how continuity is important. All right. So let's say we have this function on A to B. Okay. Well, maybe I could draw this function a little bit differently. Maybe let me draw it a little bit differently. Let me draw it in a way that it has like a absolute maximum like that. Okay, and an absolute minimum like that. like that. All right. Okay. Remember, if you have a positive function, integral of a function interprets as area under the graph. Okay? So let's look at that area quickly. Here is the area under the graph, which means really integral, right? Yep. Okay, and I'm gonna write that in and call that function, by the way, y equal to f of x. Okay, so we are looking at the integral from a to b of f of x. Let me do f in blue. So f of x dx. Okay, so the green shaded thing is the area. Now, let's pay attention to this area. This function, you guys, this function, since it is continuous, then remember from yesterday, by the extreme value theorem, it will have at least one minimum and one maximum over the interval, okay? So where is that minimum? That minimum happens to be, let's see what color to use, right here, right there. You see that point? You guys see that point? Red, in red. Y'all see that? Yes?
Yes.
That is
Yeah.
yes, that's the minimum, and it is a y value. Okay, so call it little m. Little m is the minimum of the function. When we say minimum of the function, it's the lowest y value of the function. Also, this thing has a maximum. What color do I use for the maximum? Let's say we use this orange. Here is the maximum. Okay, and I'm gonna call that maximum capital M. Capital M. Okay, so let's try to draw two rectangles here. Let's go with the smaller rectangle here. So I'm gonna draw a rectangle with a height that's the same as small m. Here is that rectangle for you guys. Why is it doing that? There we go. Okay, what is the area of that small rectangle? Can anybody tell? Look, the width of that rectangle is little m. So what's the area of that rectangle? Anybody? See, length. The length here is b minus a, right? This length is b minus a. So what should be the area of that little rectangle? Rectangle, yeah. Anybody? Let's go with who? Viviana. Viviana, are you there? What's the area of this rectangle? Anybody knows the area of a rectangle? Viviana?
Yes, Professor? Yeah.
Oh, you got a little kid? Yeah?
I'm sorry.
You got a little kid or something?
Yes.
Well, let
Yes.
the kid answer. The kid wants to answer. Go for it, kid.
Say hi.
Yeah, so the length of this, the area of that little rectangle is the height. The height is m, the length is b minus a. So it's m times b minus a, correct? Correct? Guys, come on, help me out.
Yep,
Right?
yep, that's it.
Yes, it's m times b minus a. So the actual integral, which is the area under the graph, happens to be bigger than, it has to be bigger than or equal to little m times b minus a. Okay, as we can see that the rectangle is smaller than the area under the curve. But we can come up with one more rectangle. Okay, rectangle with height that's capital M, like this. See? Like this. So I'm drawing a rectangle with height that's the same as capital M. Here is that rectangle. You see that? Yeah. So look at the area. Now look at the area of the big rectangle. Okay, the height of the big rectangle is capital M. Okay, this is capital M. The length of it is still b minus a. So what's the area of the big rectangle?
Capital M times B minus A.
Thank you, Nicole. Thank you, Nicole. Capital M times b minus a. Yes. Yup. Capital M times b minus a. And it turns out that the area of the big rectangle is bigger. It's bigger than the area under the curve. So that's an inequality. Okay. So what we have here is a bound. This gives you bound for your integration, and it's a super important, it's actually very important inequality here that you can use, that we can use for problem 3. Okay, let's do that. Okay, so remember that again, that since f is continuous on on closed interval a b, then by extreme value theorem, f has at least one min or max on the interval AB. It's guaranteed. It's guaranteed. Okay, so let's go back to this integral right here. All right. So our function here is square root of 1 plus x squared. And we are interested in this function on the interval from -1 to 1. Because the domain of integration is from -1 to 1. All right. So what do? You're going to use yesterday's methods to find the maximum and minimum of this function on -1 to 1. How do you do that? You guys who can propose, this is review from yesterday. Let's go with who did I not call yet? Diak Young Cho. Help me out here, Diak.
What did you say?
Yes. How do I find the maximum and the minimum of this function on this interval?
First of all, divided this function, and then put the 0 on x. If there are 0 on this domain, then it will be the maximum and my minimum.
So you said first of all find the critical value?
Yeah.
The derivative? Yes, let's take the derivative. The derivative here is 1 over 1 plus x squared. And then you multiply by the derivative. There's a 2 here by the derivative of 1 plus x squared, which is 2x. So this derivative is just x over 1 plus x squared. Okay. So critical value is when you set f prime equal to 0. F prime equal to 0 means the numerator equal to 0. You have to set the top equal to 0, which gives you x equal to 0. You also want to make it undefined. F prime does not exist, which doesn't have a solution. You have to set 1 plus x squared. You have to set the denominator equal to 0. And 1 plus x squared is not equal to 0. So forget about that solution. So the only critical value is, so this 0 that falls in the interval from -1 to 1 is critical value. Okay? So now you check which is going to give you max, which is going to give you minimum. So you're going to find the f of endpoints and f of critical values. Okay, so f at one of the endpoints, right? One of the endpoints is -1. Okay, so you get square root of 1 plus -1 squared, which is just √2. Find the f of the critical value, which is 0, and that gives you just √1. And find the f of the other endpoint, f of 1, which is also 1 plus 1, √2. So absolute max is at √2, absolute min at 1. Okay? Yes. Right. Okay. So also, yes, so we're done. We are done. The integral the integral from -1 to 1 of the square root of 1 plus x squared dx is bounded by, okay, it's bounded by the absolute minimum. So again, the absolute minimum, that's our little m, and the absolute maximum is your capital M. So it's bounded by little m little m is just 1, okay, times b minus a, and absolute maximum, which is yeah, that was supposed to be red. And the absolute maximum, which is capital M, and that's root 2. Okay, so you do root 2 times again 1 minus -1. Okay, so we have the answer. We have the answer. So our integral is bounded by 1 times 2, which is 2, and 2 root 2. Okay, that answers the question. Okay, very important theorem when you're finding bounds for integration. Okay, cool. Let's see, what's the next interesting problem? Some of these problems, when I was looking at them, I'm like, oh my God, they look interesting, but how am I gonna do them? I looked at these problems like 5 minutes before logging on to Zoom this morning, and I'm like, oh my God, how am I gonna do some of these? Oh my God, I'm panicking, but they're not that bad. All right, so something like problem maybe 4. I don't know which problem is cool. Yeah, so let's actually copy and paste this problem here. All right, problem 4. Fundamental Theorem of Calculus. I mean, you guys have no idea why they call it the Fundamental Theorem. Fundamental Theorem. This theorem, guys, it's gonna pop up in Math 11 also. And the way this theorem presents itself in Math 11 is gonna blow your mind. It's insane. It's absolutely insane. When you get to like 3-dimensional stuff, ooh, it'll be cool. Aika knows what I'm talking about. Anyway, they say, suppose f is continuous, of course, because we're talking about integration, and f of 4 is, find f of 4 if the integral from 0 to x of f of t is. Any ideas here? Any ideas? Let's go with Quanling. Quanling, what do you think, buddy? Quanling. Did you go?
I think we take the derivative of the function on the right side.
Yeah.
Then we get f function of t.
Yes.
But I'm not entirely sure how we deal with the bound, though.
Good. Good, man. So you said take the derivative.
Yeah,
Yes, very good. So f is the integrand of what we call an integral function. We have an integral function. Now, when you guys do differential equation, you'll be looking at a bunch of what are called integral functions. So you have functions that are represented as integrals. Okay, very good. And you want to take the derivative, really, to extract the function out of the integral. So they want you to find f of 4. Yes. So the fundamental theorem part 1, fundamental theorem of calculus part 1, says that if you differentiate an integral function from a to x of f of t dt, it gives you f of x back. Okay? Yes. Yeah. So what we do is we take this function and we are going to actually differentiate left and right hand side. So we do the ddx of the left hand side, and we do the ddx of the right hand side. Okay, so by fundamental theorem, the derivative of the left is simply just f of x. Yeah, unless you have to use chain rule. For instance, if this was a root x, okay, then the answer would be f of root x. Then by chain rule, you would have had to multiply by the derivative of root x, which would be 1/2 root x. Okay? Yeah, so, but this is simply x. Pay attention to that, okay? Some of you on the pretest messed that up. Okay, well, right-hand side, we use product rule. Take the derivative of x is just 1 times cosine x. The derivative of cosine x is negative sine x times x. Okay? Well, now I have f of x. So this is a joke. All I got to do, plug in f of 4. Okay, so f of 4 is equal to cosine of 4 minus 4 sine 4. Yeah?
Excuse me, Professor. I think the original function was cosine pi of x or x cosine pi of x.
Oh, it's cosine pi x. Yeah, I'm
Yeah.
like, what? I'm like, what the heck? Who cares about cosine of 4? Oh my god! Like, I'm like, what am I gonna do with cosine of 4, dude? Cosine of 4. I need a calculator. Okay, so cosine of pi x. Thank you. Plus, so when you take the derivative of cosine, you get negative sine. You have an x. By chain rule, we have a pi sine pi x. Now stuff makes more sense. So here you have cosine of 4 pi minus 4 pi sine 4 pi. Who cares about sine of 4 pi? That is 0. Cosine of 4 pi is, what is it, 5? I'm kidding, it's 1. 1. That's it. Okay? Yeah, so what's the next one? Next one. Find a function. It says, look at that question. find a function. They don't tell you find the function, meaning that there could be multiple functions over here. Okay, multiple functions. So what does it say? 6 plus the integral from a to x. Oops. Six plus integral from a to x of f of t over t dt equal to 2 root x. X is positive. I got that right. 6, 0, a to x ft over t dt equal to root x. So what do you guys propose I should do with this problem? And what do I need to find? I need to find a function and a real number a such that this is true. Any ideas? Ideas. Anybody? Go for it. I want you to answer it. Good question. Go.
Don't you have to change that f of t into f of x?
Well, how would I do that?
Isn't there a rule? I forgot. There's like a process by which you do it, but then you end up having a different. I forgot. It's been a while.
Any other ideas? We want to find a function f and a real number such that this is true. Ideas? What if you take the derivative again? When you take the derivative, then you are going to be able to get a function, don't you? So if I were to differentiate this with respect to x, so do d dx of the left hand and do d dx of the right hand. So what's going to happen? You get f of x over x, right? The derivative of 6 is 0, and the derivative of 2 root x is what? It's 2 over 2 root x, right? Okay, so how do I solve for f of x? F of x is equal to, just multiply both sides by x. These cancel out. So you get root x, don't you? Right? So my f of x is root x. Okay, what else?
Professor, what happened to that x that f of x was divided by?
Which x? F of x is
x over x.
Oh, let me see. Oh, right here?
Yeah, isn't it x over square root of x?
So I'm simply plugging x in here. Right?
Right.
derivative from a to x of f of t dt is just equal to f of x.
All right. No, you're right.
Yeah. So any ideas? So what's going to happen if I plug in, since I have, let's check. We have 6 plus the integral from a to x of f of t. So f of x is root x. Then f of t is equal to root t. Right? So you get root t over t dt. All right, so this is 6 plus a to x of root t over t is 1 over root t I'm sorry, this is a dt. Okay, so that gives you 6 plus the integral from a to x of, that's t to the power of negative 1/2 dt. That's 6 plus the integral of t to the negative 1/2 is t to the power of 1/2 times 2. This thing is going from a to x. Correct? So this is equal to, let's get it, it's 6 plus, did I get my 2's right? Is everything right with the integration? Yeah. So 6 plus 2 root x, okay, minus 2 root a, and I need this to equal to, so I plugged into the left-hand side, and I need the answer to equal to 2 root x. Let me move that down. Oops, hold on. Okay, so when you're solving this, the 2 root x's cancel. You get 6 plus 2 root a equal to 0. Right, what is root a? So here root a is equal to 3 divided by 2, negative 3, or 6 divided by 2, negative 3. That doesn't make any sense. I don't know what when
minus 2a, 2 root a.
Minus 2 root a. Oh yes, it's a minus 2 root a. Sorry about that. That's a minus 2 root a. Okay, so root a is equal to 3. So a has to equal to what?
9.
Yes. So sorry, this seems a little bit messy. Let me explain one more time. Here is the integral equation. I took the derivative of both sides here. Okay, the derivative of the left hand, the derivative of 6 is 0. The derivative of this integral, basically plug x for t. This is what I get. The derivative of 2 root x with respect to x is equal to this. So multiply both sides by x. That's what we get. We get f of x equal to root x. Okay. Let me erase that. All right. Now, plug this back into the integral here. Okay. So I'm plugging back into the integral. So I have 6 plus the integral from 0 to x. I found my f of t. So f of x is root x, f of t is root t over t dt. So that's that whole thing. All right. I solved this integral. So I solved it. I'm solving it. And I take this integral here and set it equal to 2 root x. And then 2 root x's cancel. I get 6 minus 2 root a. I solve for a. A is equal to 9. All right, so sorry if it was a little messy. So here, conclusion, f of x is equal to root x, and a is equal to 9. I don't know how impressed I am with this problem. Anyway, sorry, but it was a little messy.
I have a question about one part of what you did. I got the whole thing, and I think someone else brought this to your attention too, but I didn't really understand it.
Sure.
In the first, second, from the third to the fourth line, what happens to that x in the denominator?
Oh, yes. So I'll show you right now. Yeah, I show you right now. So I have this, right? I multiplied both sides by x. These x's cancel, and then you get x divided by root x. X divided by root x is equal to x. This is what I got.
Got it. Thank you.
You're welcome. I'll make sure I'll try to be neater on the next one. Okay, so that's enough of those. On the pretest, I noticed that some of you guys actually messed up the fundamental theorem of calculus, where you have to take the derivative of an integral. So let's try to work on that quickly. This problem here. Yeah. So here, you guys, we need to use the chain rule. The chain rule says if you have the derivative of the integral from, like, let's say h of x to g of x, okay, of some function f of t dt, okay, the variable of the integral is t. You're integrating with respect to t, and you're plugging these functions of x into the antiderivative, and then you're taking the derivative. Of course, you are not taking the derivative here. The answer here is equal to, well, what you do is you plug the upper function. Okay, let me use a different color here for g of x. So let's use this color. So you plug in g of x for f, okay, and then chain rule multiply by g prime of x. Chain rule. You're taking derivative after all, okay? And you are also using the fundamental theorem of calculus. So minus, take the function f and plug in the lower limit of integration, which is h of x. Chain rule it again, multiply by h prime of x. Okay, so let's do that on this problem. All right, this problem here. Okay, so our function is t sine t. You plug in the upper function, okay, into t. So you get here 1 plus 2x. So you multiply that for t, so it's 1 plus 2x. That's for t times sine of 1 plus 2x. Okay? So that's t sine t. That's t sine t. Then you need to multiply by the derivative of the upper function, which is 1 plus 2x. Okay? Minus all that, do the same thing with the lower function, with the lower expression. Plug that into t and t here. Okay, so you get 1 minus 2 sine 1 minus 2 sine x again. 1 minus 2x again. That's 4t times sine of 1 minus 2x. And then chain rule it times the derivative of 1 minus 2x. Evaluate. All right. Okay, so we get 1 plus 2x times sine of 1 plus 2x. Okay, times it now by this derivative. The derivative of 1 plus 2x is just 2. Okay, it is just here. Let me do it in this color. It is just 2. All right, don't forget the minus. Minus 1 minus 2x sine 1 minus 2x times again by the derivative of 1 minus 2x, which is negative 2. Okay, that's it. That's it. Don't drop things out. Okay, please. So some people forgot to use the chain rule on that. Okay, simplify that if you wish. Here we have a bunch of integrals. Oh God, you have no idea how important these integrals are. You have no idea, I'm telling you, man. And I hope, I'm hoping that I have enough enough time to actually do these. Yeah, so look at this integral. All you guys know how to do is substitution, okay? Substitution is when you have an integrand that is in composite form. There is an inner function, okay? Inner function. Well, here you have a square root. And guess what? Square root has stuff in it. It has stuff in it, okay? So you automatically let the stuff in there be u or v or whatever the heck you want, okay? Call that u and see if it's gonna work out. So u is a x squared plus 2bx plus c, okay? Not only you need that, you also need the derivative of that. Not only we need to substitute for x, we need to know what dx is. Okay, so find du here. Du with respect to x. The derivative of ax squared is 2ax. The derivative of 2bx is just 2b. And the derivative of c is 0. Now, guess what? Here, oh, don't forget the dx. Look at that. Look how nicely things work out. This guy, remember, pay attention, please. This guy is sitting right here looking all cute. Look, ax plus b. Here you have ax plus b. Forget the 2. You can take the 2 out. Take the 2 out. Okay? You can divide the two. You have 1/2 du equal ax plus b dx. And now substitute. Okay? Substitute. So equal to, in the denominator, you have the square root of just u. All right. Ugly, very ugly, not so ugly. Okay? The top, ax plus b dx, ax plus b dx, ax plus b dx is just half du. Half du. Look how tremendously this thing, tremendously easier this thing becomes. Half, you could kick it out of the integral. You get half times the integral of 1 over root u. You could think of it as like u to the power of -1/2 if you want. Du. Now integrate with a peace of mind. I have the 1/2 in front. The antiderivative of u to the -1/2 is u to the +1/2. And then you divide by that new power. Don't forget the constant. Okay, half and half, they kill each other, and you get u. So what was my u? U is ax squared plus 2bx plus c. Okay, that's u to the power of half plus c, and that is the end of it. I don't know why some people get so stressed about a simple substitution that takes a nightmare into a I don't know, whatever. Yeah. Integration. Let's look at the next integral. What time do I have? Let's see. Which one of these do I want to do? Let's do B. The antiderivative of x over cosine squared x squared. Where did it go? Day 5. Oh my God, I can't find my day 5. Did I close day 5? Okay, give me a second. There we go. Yeah. So what was that problem? Antiderivative of x over cosine squared. X over cosine squared x squared. Remember what I said. Hey, you guys, who can tell me, for the last integral, there was a terminology I mentioned, and it started with C. Something functions. Something functions. The integrand is A. Come on, let's go. Something. It started with a C. C-O.
And cosine function?
C-O-M.
Composite?
Yes!
Composite.
Yes, composite function. You have a composite function, for God's sake. Yep, look at that. Cosine square of x squared. X squared. Look at that. X squared. The derivative of x squared has an x, and x is sitting here looking all pretty for you. Looking all cute and pretty. Inner function, the derivative of the inner function. So why don't we do that? Let u equal to the inner function. Okay, differentiate the u is equal to 2x dx. And well, you know, as I said, I have x, I have dx, x dx. I can substitute for that. This 2 I want to kill, divide by 2. So du over 2 is actually your x dx. Okay, so the integral turns into the integral of, well, x dx, baby, is du over 2. Okay, and in the bottom you have the cosine of, I called that x squared u. Oh, and it's a cosine square of, so even better. Okay, so now look, this du over 2, this 1/2 is just a number. You can kick it out of numbers that are in an integral. Kick them out. Don't let them be. Kick it out. I'm kicking the half out. I have the integral of, and by the way, the reciprocal of cosine squared is secant squared. Okay, so we get secant squared of u. And we all know what the antiderivative of secant square u is. What is it? What's the antiderivative of secant square, you guys? Chop, chop, go, go, hurry up. Yes? Say what, say what?
Tangent u.
Yes, thank you, tangent u, with the half in front. Tangent of u plus c. And we all know what u is. So tangent, what was u? U was x squared. Okay, that's it. As easy as that. Okay, not bad at all. Yeah, so just try to do a hell of a lot of integration. So important, you have no idea. Let's jump. If you look at this problem, sine of root x over root x, you guys can do that actually. It's pretty easy. Let me see if I can do a problem or two here. Substitution rule, what do I do? What do I do? These are easy, man. Like look at this problem. Composite, look, composite. This sine x is in the belly of the sine x. Composite. So if I let this be u, the derivative is cosine x, and that's sitting right there. Composite function. Okay? Yeah. Who can tell me, you guys, who can tell me the value of this integral? Quickly. I need like maybe 2 seconds to answer this question. Anybody can tell me what this is?
I'm not completely sure. Just by looking at the limits of integration, it would be symmetrical. So would it be 0?
Yes. Yeah, very good. This function is odd. Okay? You have this function even because you have x squared, right? You have an odd, you have an even times x. right? So imagine the integral of x. Here is the graph of y equal to x, right? This is x. From negative a to a, right? This is the integral. This is positive. This area is positive. This area is negative. So yes, they cancel out. You get 0. Very good. Good job indeed. Let's do one of these also. Let's see which one I want to do here. Maybe this one. I really liked these problems when I taught Math 7. Okay, so you are given an integral from 0 to 9 of f, and then they tell you it's 10. They want you to find the integral from 0 to 3 of x, f of x squared. What's the word again, you guys? What is the C word? You guys?
Composite.
Say what again?
Composite.
Composite. Composite. F of x squared. X squared is composed into f. Composite. Yes. What do you do with composite? You substitute. Right? X squared is composite. So we let u equal to x squared. Don't forget about du. Du is 2x dx. Well then, I have this x dx here. I will be substituting for that. Okay? Yes. And that x dx happens to be half of the u. Okay, so this integral, don't touch the limits of integration yet. Okay, x dx is half du. So let's put that in. Half du, and then you have f of x squared is u, fu. Now, we need to change the limits of integration. That's so important in Math 8. People always forget to change the limit of integration when they do a substitution. And I just get so mad. No matter how often I tell them. So let's change the limits. You know, the relation here is u is equal to x squared. Okay? So these limits, these are x's. These are x's. Okay? So let's go with the lower limit. If x is 0, then u is 0, u is x squared. U is 0 squared, which stays as 0. So that 0 remains coincidentally 0. Let's change the top limit of integration, which is 3. Okay? So here, if x is 3, then u is equal to x squared, which is 3 squared. And 3 squared is 9. Okay? So what's happening here is that we have, let me move things around a little bit. Yes. So we have 1/2 is a constant in front of the integral. Take it out. The integral from 0 to a of f of u du. And, 0 to 9. I don't know why I said a. It's 0 to 9. 0 to 9. Yes, 0 to 9 here. Okay. And the problem tells you right there what the integral of f from 0 to 9 is. It's 10. It is 10. They tell you the answer already. So it's equal to 1/2 times 10. And the answer is, what's half of 10? Is it 11? Guys? I think it's 5. That's it.